Okay, so the last piece for this material is the looking at quantity discounts. As far as this is concerned, we're taking the shortages out of this. They can always be added back in, but we're going to go back to our original model, the EOQ model, and we're going to look at having quantity discounts. If you have an order over a certain size, you end up paying a smaller unit rate. So as far as this is concerned, for what we're doing here, we're going to let C of Q, our cost function for our order, be a step function. And the value C sub j is going to be the unit cost for an order in group size j. Okay, so we're going to go back and take a look at our original cost function. Remember that we were talking about a cost function t in the EOQ model. And because of the fact that we have different unit costs for different sizes, we're all of a sudden going to make this t sub j. And if you go back to our original EOQ model, we had d times k divided by q plus, and in the middle, we originally had d times c, but in this case it's going to be d times c sub j, corresponding to the appropriate unit cost, plus h times q over 2. Now for the purpose of what we're doing for this problem and for the ones you have for homework, what we're going to do is say that h is a function of the inventory value. So for the purpose of this problem, this example in this material, we're using 18.3-12 out of the book. This is on page 894. And what we've got here, if you think my jokes are bad, and I know you can't see me as I'm reading this, but if you've got your book out, it starts out MBI, IBM in reverse, is a manufacturer of personal computers. All its personal computers use a hard disk drive which it purchases from Enos, Y-N-O-S, Sony. MBI operates its factory 52 weeks per year, which requires assembling 100 of these disk drives into computers per week. MBI's annual holding cost rate is 20% of the value based on purchase cost of the inventory. Regardless of order size, the administrative cost of placing an order with Enos has been estimated to be $50. A quantity discount is offered by Enos for large orders as shown below, where the price for each category applies to every disk drive purchased. So, as far as the three levels are concerned, what we've got over here, the levels are 1 to 99, 100 to 499, and 500 or more. And as far as the price per drive, the values are $100, $95, and $90. So if this is anything close to current, apparently this company is putting 2 terabyte hard drives in their computers. Prices are a little up there. Anyway, so what we've got here, we said that the demand, if we go back to the problem here, is 100 drives per week, and they're doing this on an annual basis, so 52 weeks per year. So D is going to be 5,200 drives per year. H, as far as this is concerned, we said it was 20% of the inventory based on the value of the inventory when it was purchased. So this is going to be 0.2 times the inventory value. K is $50. And then our CJs over here are C1, C2, and C3. Okay. So if we plug stuff in here, we're going to have three cost functions, T1, T2, and T3. D times K, the number of drives per year, times the order rate, that's going to be a constant for all three. So this is going to work out to be 260,000 divided by Q. The middle term, we're going to have our annual demand times the unit price. So when the annual demand is $5,200 and the price is $100, we're going to add in $520,000 here. When the unit price is $95, this is going to be $494,000. And when the unit price is $90, this is going to be $468,000. Okay. Now, as far as the last piece is concerned, when the price of a drive is $100, H works out to be $20. So if we were to plug 20 in here, we're going to have 20Q over 2. Oops. So this is going to be 10Q. In the second case, instead of 20 up here, it's going to be 19. That's 20% of 95. So this is going to be 9.5Q. And then lastly, when it's $90 a drive, this is going to work out to be 9Q. Okay, so we have these three curves, these three cost functions here, and make sure I've given you enough time to write these down. The thing that you have to recognize with these functions visually essentially, if this is T up here and this is Q down here, the shape of each of these functions, if you were to graph them, looks a little bit like that. Okay. And because we've got three of these functions, all we're doing is we're changing the coefficient on Q. We're raising this constant. This term remains the same right here. So effectively what's happening with these functions is they're the same shape for the most part, but they've been shifted. So this is just an approximate. I'm giving you an idea here. And so as far as we're concerned here, the thing about this is that we have to remember that T1, our order size here, this is with Q less than or equal to 99. This is with Q between 100 and 499. And then this is Q greater than or equal to 500. So based on what we're seeing here in this graph, it appears that the optimal value is right there. That's going to be Q star. But we don't know which interval Q star falls in. So we're going to have to take the derivative in each case, set t sub j equal to 0, and solve for Q. And then essentially, if you were to think about the situation where, let's say that the splits are there and there, and let's say that this is T1, T2, and T3, then as far as T1 is concerned, even though the optimal value over the entire function is right here, our optimal value is going to be right at that border, which is 99, at least over the 99 and fewer range. That's where we'd find our optimal value. For T2, it would end up being right here, because that is the minimum within that range. And for T3, it would be at this borderline right there. So we're talking about finding, in some cases, the global min, and in other cases, the local min. So, for this purpose, if we do, oops, on D, I goof. If we do dtj dq equal to 0, what we end up having for the three cases in terms of the global mins would be q equals 161.25. This is for j equals 1. For q in the second case, it would be 165.43. And in the third case, it would be 169.97. So this compares to the drawing that I gave you right here. So as far as j equals 1 is concerned, what we have to do is we would have to use q equals 99. For the third case, we would have to use q equals 500. And since we're talking about hard drives here, in this case, we would definitely have to use q equals 165. At that point in time, what you're going to do is you're going to go back and you're going to plug the corresponding values of q into the three different functions here. So we're going to plug 99 into T1, we're going to plug 165 into T2, and we're going to plug 500 into Q3. And if we do that, what we end up getting for costs for T1 at 99, we get $521,016.53. T2 at 165, we get $495,130.49. And for T3 at 500, we get $472,501.04. So as you can see, the drawing that I gave you here, what we're basically doing here is we're saying, here's the best situation here. So this right here is T1 of 99. This right here is T2 of 165. And this right here is T3 of 500. And matching up with this diagram, you can see, although it's certainly not to scale, that the smallest of these three values occurs at T3 with an order size of 500. So our optimal order size here is going to be 500 at a cost of $90 per disk. And our total annual cost for this ordering policy works out to be a little bit over $470,000. This ends the inventory theory portion. The beginning part of Chapter 18. Next week when I'm back, we'll go ahead and move on to a couple more of the deterministic models. But for now, have a good week, and if you haven't taken it yet, good luck on the exam.